So up until now, the forces that we've been dealing with have been responsible for generating linear motion. What we're going to do is we're going to talk about a different type of force that instead of causing something to accelerate, along a straight line, causes something to change directions. So let's start by sort of in its most basic form, things that move in circles. The easiest way, or the easiest type of circular motion to deal with, is uniform circular motion. So uniform circular motion, the uniform tells us it's at constant speed, and so you notice here I've got a velocity vector at all four of these points. The magnitude of that velocity vector is the same. So here's an object that's circling around. The circle it's traveling on has radius of r, and it's traveling at a uniform speed. And I know that because the magnitude of the velocity vector isn't changing. So the uniform tells me constant speed. And then the circular says, hey, you're moving along a circle, or the arc of a circle. In this case, we're moving along the full circle. And so if we've got motion with constant speed, well, we know how to deal with that. We can say, hey, the speed you're traveling is just the distance divided by the time. The distance, if you're moving around a full circle, is 2 pi r, and the time here is t. So capital T is what we're going to use to talk about the period of motion, and the period is just the time to complete one cycle. So basically, if we were to start our clock when our object is here, the period is how long it takes for the object to go all the way around the circle and end up right back where it started. So you notice we can rearrange this equation and basically say, well, the period then is given by the distance it travels divided by the speed it's going at. So here's 2 pi r to go around the circle, and then here's the speed that it's traveling around the circle. So why do we have uniform circular motion? Well, basically we have uniform circular motion because there's a centripetal acceleration. So here's a situation where we've talked about acceleration can do one of three things. It can force an object to speed up, it can force an object to slow down, or it can force an object to change its direction. And so for uniform circular motion, what we've got is we've got an acceleration that is always causing our object to change its direction of motion. Speed stays the same. It's not speeding up or slowing down, but the direction it's changing is always different. So with centripetal, basically is a translation that means towards the center, to go to the center. And you notice that the centripetal acceleration always points towards the center of the circle. So one of the things that's going to be nice about working centripetal motion problems, because again, they're really just Newton's second law problems, but they're Newton's second law problems that are easy to identify the direction of the acceleration because the acceleration is always going to point towards the center of the circle. How do you calculate the centripetal acceleration? Well, the magnitude of the centripetal acceleration is given by the speed squared divided by the radius. And so again, the nice thing here is if you can figure out where the center of the circle is, which again, usually given the motion you can, then picking at any point the object is where it travels around this circle, it's always easy to identify the direction of the centripetal acceleration. And we know that identifying the direction of the acceleration is one of the key things we want to be able to do when working a Newton's second law problem. So what causes a centripetal acceleration is a centripetal force. So basically what happens is the centripetal force is really just another way of saying what's the net force that causes the object to go in a circle. So the centripetal force is not some new force, right? So when you look at sort of these two equations sitting side by side, right? The centripetal force is equal to mass times the centripetal acceleration. Well, we know that Newton's second law is that the net force is equal to mass times the acceleration. So what this means is that the centripetal force is really just another way of talking about the net force whenever your acceleration is centripetal. So if you've got an object that's moving in a circle, the centripetal force is just a way of talking about the net force. So these are all forces that we draw in our free body diagram, right? We put the weight, the normal, friction, tension. We'll put spring forces in there eventually, applied forces. All these forces go into the free body diagram. The centripetal force does not. We're never going to draw the centripetal force into a free body diagram. Instead, what we're going to do is recognize that the centripetal force is just another way of saying the net force in a problem where you have an object undergoing centripetal motion. So the easiest way to calculate the magnitude of the centripetal force is just calculate mass times the magnitude of the centripetal acceleration. And we know that this is v squared over r. So mv squared over r is the easiest way to calculate the magnitude of the centripetal force. That's what it has to be.